Hello everyone, this is the video lecture of section 6.3 of ordinate differential equation, math 2540. Okay, this is a lecture for the class on Thursday, April 2nd. Okay, so I just summarized what we learned in section 6.2 from the Monday lesson and the last Thursday lesson. Monday, March 30th, and actually Friday lesson, 27th of March. Okay, so when you had a homogeneous linear differential equation with constant coefficients, we introduced this differential operator using d as d over dx or d over dt, differentiation n times, nth order derivative. If you write it, and then you can write this differential equation as L of y equals 0 by introducing linear operator L. Now, this is closely related to characteristic polynomial, a(n) r to the n, a(n) minus r to the n minus, so using the same coefficients in the differential equation. And then your L is just P of d. Replace r with differential operator d. All right? And then, using those fancy notations, we were able to show the following things systematically. Basically, this is the same idea as section 4.3. But because we are dealing with general number n can be any high integer number, so it was necessary to develop this fancy notation to deal with this for general n value. First of all, if your L can be written factored this way with distinct Ri's. That means your characteristic polynomial can be factored into the n distinct linear factors. So characteristic equation has a n distinct solutions, either real or imaginary. Then these e to the r1x, e to the r2x, all the way to e to the r1x are all linearly independent solutions to this equation. So to get the general solution, you just make linear combination of those. Now, if some of them is imaginary, let's say one has alpha plus beta I, then one of the other must be complex conjugate. Because AIs are real coefficients, real coefficient polynomials, if they have imaginary solution, its complex conjugate must be a solution too. They come in pair. Now, I just noted here, in order to get alpha plus beta I and alpha minus beta I as a solution, actually, that should come from this quadratic factor. So I'm going to show you briefly. So if you have a R minus, so one of them is this. R minus Rj will be this, right? R minus alpha minus beta. So R minus Rj, R minus Rk. Now, we want to write this one as this way. As alpha plus beta I. And then we use a minus b times a plus b as a squared minus b squared. Comes from here. So that means if you combine these two terms, which are source of the complex conjugate roots, that would be d minus alpha squared plus beta squared. Okay, so one of those ones come together, Rj and K together will be same as this if you combine them. All right. Or you can show that starting from here, you can get R equals alpha plus minus beta. Anyway, okay? So having imaginary solution means having this one, part. Okay? All right. So it's better to write it. That means d minus Rj times d minus Rk, Rk rk will be d minus alpha squared beta squared. That's what it means. Okay. I'm going to erase this. So, what if you have repeated zeros? Let's think about this one repeated. D minus R1 to the mth power. Okay? So R1 is repeated n times. In that case, just like in second order case, not only e to the R1x, but x times e to the R1x is a solution. If you have n all the way to x to the n minus 1 power times e to the R1x. Also, the solution. So actually 0, 1, 2, all the way to n minus 1. Totally m solutions, linear independent. So general solution can be written as C1, linear combination of this. A lot of times we write it this way. E to the R1x, and write it C1, C2x, C3x squared cubed, all the way to Cn, x to the n minus 1. Okay? That will be better looking, more organized. Likewise, if alpha plus beta I and alpha minus beta I are both repeated roots of the multiplicity m, that means you have d minus rj to the m power, d minus rk to the m power. Each of them repeated m times. What that is d minus rj, r means this, rk means entire to the mth power. And we just found that this is d minus r squared beta squared to the mth power. That's why I wrote this. So this means that both n have multiplicity m. That's the case. In that case, just like you have x squared times in front of this one working, you have x times this one, x squared times this one, all the way to x to the m minus 1 times this one. Same thing for e to the first sine beta x. So you have a totally 2m, totally 2m solutions. So 2m solutions here too. All right? Okay, so this is the grand summary of what you did in long section 6.2. That was very theoretical and hard section. That's what we covered it over 2 days. Last Friday, March 27th, and last Monday, March 30th. Okay? Now, we are going to change our perspective slightly, our viewpoint slightly. So, if your L has like this, L of y, so that means if L equals d minus r1, that means that the solution is this, means that e to the r1 x must be 0, because this is a solution, right? If r1 is a root of Peretti equation, then e to the r1x is a solution of this one. That means when you plug it in, you get 0, right? So that's what you see in the first page of 6.3 lecture notes. If f of x is e to the rx, linear differential operator d minus r, this is our L, right? This one, all that function becomes 0 because it is a solution to this differential equation, right? If your L is just the first one. Yes. Now, as you can see, x to the k e to the r1x from 0 to up to m minus 1 is a solution to this, right? That's why if f of x is x to the k e to the rx, where k can be any integer between 0 and m minus 1, then d minus r to the mth power. Instead of r1, I have just r here. That is a solution to this, right? According to this observation, will be 0. Means this is a solution for that equation, that linear differential equation. Okay? And as you can see here, if f of x is e to the alpha x cosine beta x or e to the alpha x sine beta x, these are the solution of what? D minus alpha squared plus beta squared of f. Okay? This is a solution for this linear differential equation when your L is of this form. Okay? Which means your corresponding characteristic polynomial will have an alpha plus minus beta I as a solution. Okay? Finally, if your f of x is x to the k power e to the alpha x cosine beta x or x to the k e to the alpha x sine beta x, either this one or this one, for integer k between 0 and m minus 1, up to m minus 1. All of those are solution of this linear differential equation. Multiplicity m will be 0. Okay? So, now, so far we said that e to the Rx is a solution of this differential equation, right? This differential equation means that when you replace y with f, you get identically 0, right? This is also a solution for this differential equation. Means that when you're plugging in this function for y, substituting this function for y, you get identically 0. This being a solution for this differential equation. We want to write it, this linear operator annihilates this function. This linear operator annihilates this function and this function. It's the same thing, but different way of saying it, right? So e to the alpha x, some function is a solution of differential equation L of y. Then we say L is an annihilator of the function. A function is a solution of L of y equals 0. We say L is an annihilator of the function. Okay? So, with this one in mind, we'll define annihilator. So, you see, a linear differential operator a linear differential operator A is an annihilator. A-N-I-H. Annihilator of function f, or is set to annihilate f. Same thing. If and only if a of f is identically 0 for all x. Alright? Which means that f of x is a solution to this linear differential equation. It's like this. Instead of L, it's any linear operator, differential operator. Okay? So, annihilator. Okay? F is annihilated by A means f is a solution of A of y equals 0. So example 1. Find the annihilator. A. X times e to the 3x. Well, we know that d minus 3 e to the 3x equals 0, right? Corresponding characteristic equation is x r minus 3 equals 0, so 3. All right? When you have x, you have to at least square of 2, right? So the annihilator must be d minus 3 squared. Okay? Then it becomes a solution for not only this one is 0, but also up to x times e to the x equals 0. So this is m equals 2 case. So k can be either 0 or up to 1. Alright? So this is the annihilator. Okay? So our annihilator, I'm going to put A1, is d minus 3 squared. What about x squared e to the x sine of 2x? Well, we know that this is alpha equals 1, beta equals 2. So look at that. Imagine a solution case. D minus 1 squared plus 2 squared. That would kill, annihilate, e to the x sine of 2x. In order to have x squared times this to work, it has to be at least 3 or more. Right? So your annihilator has to be at least multiplicity 3. It's not here. At least 3. Okay? C. What if you have 2x e to the 3x plus minus 5 x squared e to the x sine of 2x? Well, in that case, it's not a1 minus a2 or anything. You have to consider a1 and a2 together. Okay? I'm going to call it, claim is that we know that this linear operator is commutative when you have a constant coefficient. Okay? With constant coefficient, obviously. Then if you combine this one to because it's linear operator, you can split over constant coefficient. Constant coefficient can be taken out of it, minus 5, and a1, a2, x squared e to the x sine of 2x. Alright? Now, a2 kills this one, but using commutative law, I'm going to write it as a2a1 of 2x e to the, no, 2 is taken out. X e to the 3x. Now, this one, what does it mean by product of two operators? That means a1 after you do a2 of this one. Alright? Then what do you get? This is annihilated, 0. Right? And this one, a2 of a1 of x e to the 3x. Also, it is annihilated. So the whole thing will be 0. So when you have a linear combination of two different kinds of functions, if you want to find the annihilator, then you have to find annihilator of the first term, and annihilator of the second term, and make a product of those two annihilators. It's not really a product, it's a composition of annihilators. Okay? All right. So, now let's do some of this here. I hope that you get this one. All right. So, second page of your lecture notes. Let's consider this one. Now, this section, we want to find the method of getting particular solution for linear differential equation, non-homogeneous linear differential equation with constant coefficients. Okay? Now, this is what we call 1 here. That means this is f of t, right? Where this is this. Okay? So 1 is equivalent to saying L of y equals f. Okay? For all x. If I use t again, well, you can use t or x, whatever. Now, suppose that A is an annihilator of f, i.e., A of f, make it a constant zero function for all x. Okay? Completely annihilates in an interval where these coefficients are some interval. Then what happens? Okay, then what happens? Say, if y is a solution to 1, then if y is a solution to 1, then A of L together of y will be A of Ly, right? A of f, which is 0. So if y is a solution for this homogeneous, non-homogeneous linear differential equation with constant coefficients, then y is a solution to this. Okay, let's say I1, yp. Let's call it yp. A particular solution to this. Okay, particular solution to this one is Lyp. So then yp is a solution to this differential equation. This is now homogeneous. This is homogeneous with higher order. Because A has also some derivatives there. So this is very important findings. A particular solution for non-homogeneous linear differential equation with constant coefficients is actually a solution of another homogeneous equation. Now, if your f is one of these kind of functions, e to the something polynomial and or e to the x cosine and e to the x sine, then A will be also constant coefficient. Then your yp will be also a solution of bigger homogeneous solution. So all the techniques we used in the previous section can be deployed to find a particular solution. This is the key. So we want to use homogeneous equation techniques to find non-homogeneous solution, a particular solution for non-homogeneous equation. All right, so we're going to call it for all x2. Okay. All right. So let's use example 2. Find the general solution of the homogeneous equation. Well, find the particular solution. Basically. Find a particular solution of A. Y double prime minus y equals cosine of x. You know what? I should have done this one 2 parts, three parts. Same thing for x e to the 2x. and then C. So this treatment will be slightly different from your lecture notes. Okay. I'm going to keep this one because that is the most complicated one. So, okay, A. So we have to find A. Which one kills cosine of x? Think about it. Cosine of x is e t 0x cosine 1x. Alright? So it's corresponding to r equals 0 plus minus I. Right? So d squared plus 1 is corresponding to this, right? Therefore, our annihilator should be this, at least you have this one, d squared plus 1. Okay? And, your L is d squared minus 1, d plus 1, d minus 1, obviously. So, our bigger homogeneous equation, for which our particular thing is the solution of, will be A L of y is actually d plus 1, d minus 1, d squared plus 1 of y. Okay? Therefore, let's solve it. Then your y should be, from the 6.2 material, what is it? C1 e to the negative x plus C2 e to the x. C3, 0, see, cosine of x. This one is r equals plus minus, and this cosine x is sine of x. Okay? Now, if you have a y double prime minus y equals 0, then your general homogeneous solution will be C1 e to the negative x, C2 e to the positive x. That would be homogeneous solution, right? So, this is homogeneous, then this must be our particular solution, right? L of y will be, this one will be 0. L of this must be cosine of x, right? So, from this, after you recognize a solution from the homogeneous equation, you recognize which parts will form a particular solution. So, we set y particular solution. I'm going to call it yp1 as c3 cosine of x, c4 sine of x. Now, we have to determine c3 and c4 by plugging in here. Okay? So, yp1 prime is minus c3 sine of x, c4 cosine of x, yp1 double prime minus sine of x. So, from L of yp1 equals cosine of x, okay? We want this to be a particular solution, means that what? Yp double prime minus yp1 equals cosine of x, right? We have to satisfy it. Just plugging it back to the equation, original equation. Then what do you have? Minus 2c3 cosine of x minus 2c4 sine of x. for all x, in order for this to happen, this has to be 1, this has to be 0. So C3 must be negative 1/2. Okay? So we find that this is negative 1/2 cosine of x. Okay? Alright, so I'm going to write it here. C equals y. Rewrite it. So here we just found particular solution for this one is negative 1, particular solution is minus 1/2 cosine of x. Okay? Now let's find particular solution for this one. So we know that d minus 1 kills e to the x. Therefore, in order to kill this one, is it 2x or just x? It was 2x, I'm sorry. 2x, then minus 2. Then d minus 2 squared will kill this. So our annihilator will be d minus 2 squared. And then our y particular solution is a solution to a to L of y equals 0, which is d minus 2 squared, and L was, we found it previously, d plus 1, d minus 1 of y. Okay? Again, we're going through this particular solution of L of y equals f is a solution for a L of y equals 0, a being an annihilator of f. So y will be again from c1 e to the minus x, c2 e to the positive x plus. Now, when you have this, you get e to the 2x c3 plus c4x times e to the 2x from the multiplicity 2. Again, this is a homogeneous solution. This must be our particular solution. Okay? It's our particular solution. So, in this case, we set y particular solution to be c3 c4x e to the 2x. So what is yp2 prime? Okay, we have to use product rule. That is c4 f prime g plus f g prime. So you can write it as c3, 2c3, c4 times e to the x, and 2c4x of e to the 2x. Okay? 2c3 e to the 2x, 4 e c4 e to the 2x combined as a constant. Then yp2 double prime will be f prime. That would be just this. Fg prime. So it will be 2c3 plus twice 2c4 twice 4c4x e to the 2x. Okay? So what is it? This is what? 6C3, right? Did I make a mistake somewhere? Let's see. F prime G F G prime. 2C3 C4. 2C3 C4 F prime. C4. Two C3 C4. Ah. Two C4. 2C4. Let's see. So, let me check recording. Okay. I think I found a mistake. This is C4, actually. I'm copying this one, factoring out this 2 times this. So it's gonna be 4C3 plus 4C4, 4C4x e to the 2x, right? Now we want to plug in into this original non-homogeneous equation. So we want to say that yp2 double prime minus yp2 equals x e to the 2x, which means this one. Or C4 x e to the 2x minus yp2. Equals x times e to the 2x. To combine it, you have 3C3 plus 4C3 plus minus C4x plus 3C4x e to the 2x equals x times 2 to the x. That means this must be 0, this must be 1, right? So C4 must be 1/3, plug it in there. 3C3, 1/3 plus 4/3 equals 0. C3 equals -4/9. All right? -4/9. So your P2, yp2 must be -4/9 plus 1/3 of x e to the 2x. Okay? So what we found is this. In this problem, what did you find? If L equals d squared minus 1, we found that L of yp1 equals cosine of x. L of yp2 equals x times e to the 2x. Now this one is what? From A and C, B, all right? Where your equation is cosine of x plus x e to the 2x. You remember superposition principle of non-homogeneous case, general case, that is P1 yp2 must be plus Because it's a linear operator, it must be cosine of x plus x times e to the x. Therefore, our particular solution for this is nothing but the first same linear combination of particular solution. What was yp1? Negative 1/2 of cosine of x. This one, 9/4, 1/3 of x, e to the 2x. So that would be a particular solution. Okay? Therefore, they ask you to find general solution. General solution is just homogeneous solution plus particular solution, right? After you find it, right, C1 e to the minus x, C2 e to the positive, plus minus particular solution. Okay? The process we went through to get this one, determining C3 and C4, is called undetermined coefficient method. All right? So, what we have done here so far is, in order to find a particular solution for non-homogeneous equation, we found the annihilator of the source function f, and then consider the bigger homogeneous equation AL of y equals 0. From that general solution of AL of y equals 0, we take out the part from the general solution of L of y equals 0. So general solution of homogeneous equation, take it out. The remaining will be a form of particular solution. But that involves some constant, arbitrary constant. And then you put this one that form of particular solution into the original equation, and then match the coefficient to determine those undetermined coefficients. That's what we did in here and here. Okay? So that process, getting the form of particular solution is annihilator method. And then put that form into the original equation and then compare the coefficient, and finding the value of those undetermined coefficients is called undetermined coefficients method. Okay? Now if your source functions is made of linear combination of completely different type of functions, then you want to find particular solution for each type separately. That would be much easier to deal with at the same time. As a note, if you have like 3 and 2, right? Then you need to have a 3 and 2 here, right? So you will have just 3 and 2. 3 times this, 2 times this. Just the same kind of linear combination. All right? So as a final thing, let's example 3. Find only the form of particular solution using annihilator method to this. D minus 1 square, D plus 1 square plus 4 cubed of y equals x squared e to the x Okay. For this one, of course, we're not going to find exact particular solution. We want to find only the form, a form of a particular solution using annihilator method. We are not going to go through undetermined coefficient method. That would be terribly large system. This is our L. All right? This is our F. First of all, you want to find annihilator. Okay? First of all, we want to find homogeneous solution, homogeneous case. So, from here, look at this. Characteristic equation will be r minus 1 square, r plus 1 square plus, this is 2 square, equals 0. From there, r equals 1, 1, see? This one is double root. Here, triple root. Which one is triple? -1 plus minus 2i. Triple root. So because of that, you will have homogeneous solution will be what? The homogeneous solution will be what? Y equals C1 plus C2x e to the 1x, right? Double. Triple. C3, C4x, C5x squared times e to the minus x cosine of 2x plus C6 plus C7x plus C8x squared to count for these 6 roots. Triples, a pair of triples, countless conjugate roots. That would be our homogeneous solution, right? Then we have to find annihilator. Now you have 2 different kinds. So we have to find 2 different annihilators. Okay, what do you get? The minimum annihilator for this one, minimum will be d minus 1 squared, and we need cube, right? D minus 1 cube. Okay? Equals 0 if this one. Now what about this? X times e to the minus x. If minus 1 plus minus 2i. Again, same thing as this, right? If a2 equals d plus 1 plus 4, 2 squared, then this will be 0. Okay? Then L of y equals f means a1, a2, L of y equals 0, right? This is the things we have been doing here, all right? So what is a1, a2, and L? Look at this. L, you have a d minus 1 square already. And, okay, I'm going to just write it, copy. D plus 1 squared plus 4 to the third power, and d minus 1 to the third, and d plus 1 squared to the square. So in the end, d minus 1 to the fifth power, d plus 1 squared plus 4, also fifth power. All right? Then, the general solution for this one is of y equals 0 means this. Okay, I'm going to write it using d. d1, d2x, d3x squared, d4x to the third, d5x to the fourth times e to the x, because you have 5. You have 5. Another 5 from e to the minus s cosine 2x and sine 2x. So, plus d6, d7x, d8x squared, d9x cubed, d10x to the fourth, e to the minus x cosine of 2x, right? And d to the 11, 12x, 13, 14, 15. That would be the general solution of this bigger homogeneous equation. All right? Now there, what did we do in the previous simpler problems? This includes homogeneous solution of L of y equals 0 and particular solution L of y equals f. So we have to take off homogeneous parts. What is it? Look at this. This one was coming from homogeneous parts, right? And up to this one was coming from homogeneous. So we can choose our particular solution to be remaining ones. I'm going to write it x squared. Square times d3 plus d4x plus d5x squared e to the x here, x to the third, d9 plus d10x plus also the other one was the same thing. Okay. d14 plus d15 of x. That would be a form of our particular solution. Okay? All right. You know, if you didn't have this d1 minus squared, which is also related to this another d1, d minus 1 to the third power. If you didn't have this one, you would have just 3. You would just have just this one, right? Without this one, you would have only this, without x squared, right? Why x squared is there? Because you have square here. Without that term, you would have only this. So having x squared e to the x involves all the downwards, x to the e to the x, and just e to the x. You can't have just x squared e to the x alone. You have to include everything down, according to annihilator method, right? Another thing is that if you hadn't had this 3, you wouldn't have this 5. You just would have only 2. You would have only these, right? Without this. This is coming from this duplicate of the same thing. So when same form of the annihilator shows up in the original L, that adds this number in front. Okay? That's the biggest observation we have. So that's why now we can say this. Final summary from these examples is the method of undetermined coefficient method. If L of y has, c times some constant times x to the m e to the rx, all right? Then yp must be x to the s c0 plus c1x plus c2x squared all the way to n minus 1, no, nx. You have to have all of it, not only x squared, but starting from the beginning. Part of the this, where s equals 0 if r is not a root of characteristic equation. So, but L does not have n d minus r, or multiplicity of r in the characteristic equation or auxiliary equation. Or previously, d minus 1 was the double root of the original in the previous example. That's why you have 2. That same order, same multiplicity in L should come over here. Likewise, if you have C, some constant times x to the m e to the alpha x cosine beta x, or sine beta x, or both, these are the same kind, right? Then your particular solution must have xds cm x to the m e to the alpha x cosine beta x. You have to have both, not only e to the alpha x cosine beta, you have to have both because they come together. Where? Same thing. S equals 0. If alpha plus or beta I is not a root of characteristic equation, or the same multiplicity of L plus beta I in the characteristic equation. So this is the conclusion, right? Now, on final exam, I don't want you to memorize and then write this one right away. I will specifically ask to show, find the form of particular solution through annihilator method, okay? It's not just the memorization. So you have to go through this. But then, understanding the conclusion definitely helpful. Alright? Alright, that's the end of section 6.3. This is the lecture for the class on Thursday, April 2nd. So by the end of the week of March 30th, you should be finishing. You should finish, and the homework problems, everything, 6.2 and 6.3. Again, we have Zoom office hours every Monday and Thursday from, I believe, did I say 11 to 12? Yeah, 11 a.m. to 12. Okay, twice a week. So I'll be waiting in Zoom meetings. So if you have any questions about homework problem or any questions about lectures and everything, just come to the meeting. All right? Okay. Well, thank you and see you next time.